Hello again, everyone, and welcome to today's webinar. Our webinar today will be a panel discussion and presentation, which will introduce how teams are balancing cost, performance, and carbon when selecting materials, and what's actually working when it comes to real projects. My name is Mariah. I'll be your host. I am the program manager for Retrofit Assist, run by Community Energy Association. If you haven't met us before, I'll introduce you to a bit of what we do in a few minutes here. So just a few things before we get started today. First, we'd like to take a moment to extend our sincere gratitude to our webinar sponsor, McDonald Mechanical. Next, I'd like to share that I'm joining you today from what's now known as Whitehorse on the traditional territory of the Coen and Dan Thompson Council. I am very grateful that I get to spend each day on this beautiful land surrounded by forests, mountains, and water. We like to start our sessions by recognizing Indigenous leadership in the built environment space. The Sechelt Nation's traditional territory is located on the Sunshine Coast of BC between what is now known as Jervis Inlet and Howe Sound. In 2023, 59 homes in Port Moody on the Lower Mainland were slated for demolition in preparation for the Inlet District Redevelopment Project. The Sechelt Nation acquired 10 of these homes that were identified by the company Renewal Development as suitable for rescue, relocation, and repurposing. In 2024, the homes were relocated by truck and barge to Sechelt, where they underwent energy efficiency upgrades and renovation to create two-story intergenerational homes within the nation's Selma Park subdivision project. Where possible, the upgrades were completed using existing cabinetry and appliances from the 49 homes that could not be salvaged. Through the leadership and collaboration of the Sechelt Nation, Renewable Developments, and West Group Properties, this project saw multiple co-benefits, helping to address the nation's housing crisis, support Indigenous families and elders, reduce costs, limit waste and embodied carbon, and reduce the need for new materials. As mentioned, I'm a program manager with the Community Energy Association. For those of you who may be newer to our work, CEA is a nonprofit that partners with local governments and Indigenous communities across BC to support practical climate and energy solutions, particularly in the building sector. A big part of our work focuses on helping the construction industry adapt to rising energy performance expectations. That includes everything from training and capacity building to coordinating conversations like this one, where we can share lessons learned and hear directly from industry. We've been delivering high-performance building training since 2017, working alongside industry associations, educators, and practitioners to make sure content is grounded in real-world application and not just theory. If you'd like to stay connected to future sessions or resources, you can find upcoming events at our website or register for our high-performance building newsletter, and you'll see those things pop up in our chat shortly here. Before we dive into the main part of our webinar today, I just wanted to emphasize that CEA's priority is to create a safe space for all folks on today's webinar. We have zero tolerance for any kind of harassment towards our staff, speakers, and other attendees, and we reserve the right to remove anyone from today's session who does not adhere to our webinar guidelines shown on the screen here. Onto the next slide. And with that, we can dive into today's session. So today's session will be a combination of a presentation and panel discussion. We will start with a presentation from Elisabeth Baudinead, founder and principal of CarbonWise. This presentation will be on choosing materials for a high-performance home. And then we will invite experts Mike Coen, Erica Wolowidnyk, and Dan Thompson to join us for our panel discussion. There will be time at the end for questions, so please make sure that you're using that chat function in the meantime. Okay, with that, I will pass things over to Elisabeth.
Thank you, Mariah. Welcome, everybody. And bright and early this morning, I see people still trickling in. Very excited to be presenting on materials that improve energy use and reduce emissions, a topic that has been dear to my heart for many, many years now. And I want to get us started by asking the questions, are energy efficient homes always better? And that's really how I started thinking about this years ago. I'm actually a former employee with Community Energy Association, and at the time we worked on the first local government guide for embodied carbon and embodied emissions. And so very, very happy that, you know, the conversation has gone a long way in the past 5-6 years now. But we keep coming back to this question about, are energy efficient homes always better? And that's really the core of this presentation today, is understanding what that means, what are energy efficiency measures that also reduce carbon, and introducing the topic of life cycle thinking and embodied carbon. And so I'll dive right in. We are energy advisors, and we see a lot of things on site and during projects. And some things that tend to go wrong are when homes are not treated as a whole system. They can be treated as just a collection of specs versus just the house as a system. And that's when we really see problems arise. And that's coming from the fact that some people think that we need to max out every single metric into the energy efficiency space. And so I'm gonna show you why this is not necessary, first of all, but also what we're on real projects, what that actually means to optimize a building versus maxing out every single metric, and what that means in practice. All of that started from this conversation about life cycle thinking, and we have run some numbers on a single family home and a duplex, looking at minimum code all electric, and looking at net zero or passive house standards. And the numbers are shown here on the left. The minimum code is actually lower life cycle carbon over a 60-year life cycle emissions time frame. And when we looked at this, first of all, I had a hunch that this was going to be like this for years and years. And then we finally got to crunch the numbers here. And I wasn't too surprised to see this. There are a few reasons for why this is happening. First of all, I must mention this is a minimum code in the city of Vancouver modeled. So the minimum code is already really good. Like, we have to acknowledge this is any energy efficiency policies, regulations, efforts that have come that have been done over the years have come a very long way. And what led us here is not what is going to lead us there. That's always what I say, is it's because we have done all of those great efforts in energy efficiency that we can see this minimum code here being very low in operational emissions in orange, because we are looking at an all-electric minimum code home that is already, has a strong envelope and airtight. So this is important to acknowledge, because, I'm not saying we shouldn't be building energy efficient homes at all. The second thing is, when we looked at extreme energy efficiency, there is a possibility that it can add carbon. It's not always the case, but there is a possibility. Because on BC's grid, and this conversation could be very different in another province, on BC's grid, the 60 years of operational savings are very small. And so any extra material that goes into making this home extra bit more energy efficient then has a bigger impact proportionally. And so this is just really an intro slide to look at the consequences of that, and how we need to move from just thinking energy efficiency to thinking about embodied carbon as well. And so, quick definition check, because those two terms often get confused. Operational emissions are anything related to operating the building or running the building over its lifetime. So this is heating, cooling, lighting, equipment use over time. Those emissions happen every single time you turn on your furnace, and those are recurring emissions. So every year, every day that you turn on any equipment, those are operational emissions, as opposed to embodied emissions, which are often hidden and not as tangible for homeowners, for example, to grasp, is that embodied emissions are embodied. The term embodied comes from embodied in the materials and processes. So those are all the emissions related to manufacturing, so mining, raw materials extraction, processing, transport, installation, and decommissioning. So most of them happen upfront before any operational savings can offset them. And on a dirty grid, for example, operational savings will dominate, right? Every time you turn on your equipment, you will emit more greenhouse gas emissions. But on BC's grid, embodied emissions become the dominant variable here. And all of that is really a question that we can ask ourselves in design and procurement stage. And of course, there is the end of life emissions, which are what happens after a home is demolished. Are we sending everything to the landfill? This has an impact as well. And I'm very happy that Mariah shared the example of the relocation of homes, because that is one of the strategies, and if not the first one on the list, to avoid those end-of-life embodied emissions. So just so we are aligned moving forward, when we talk about carbon in buildings, we are thinking about those two sides. So there is the operational carbon, emissions from running the building, and embodied carbon on the other side, emissions from materials and processes. On the left side, operational intensity is how we divide operational carbon by the floor area. And similarly, embodied carbon intensity is the total embodied carbon divided by the floor area. Operational carbon gets modeled with an energy model. And that's how we measure buildings' energy use and operational emissions. And the tool to measure embodied carbon is a life cycle assessment. So side by side here, this is what it looks like. I'll say that the zero carbon step code, the terminology is so confusing sometimes, flagging that the zero carbon step code in BC is only related to operational emissions, not embodied carbon, even though I know the terminology is confusing. I didn't make that name. So most of what is regulated currently in BC and across Canada is related to operational emissions. We are slowly seeing some jurisdictions taking the lead on embodied carbon. And so you're probably familiar with most of those metrics. But when we start thinking life cycle thinking, I'm adding the materials here at the end, so I'll just go over them one more time. First, when we talk about high performance, energy efficient buildings, we always talk about airtightness. For me, that's number one, and I'll show you why in a second. So airtightness is one of the metrics to achieve the BC Energy Step Code and high performance standards. And so it is measured ACH at 50 pascals, air changes per hour. Then we have our envelope. Envelope is the TEDI, and that's anything walls, windows, roof, that's the building envelope. We have mechanical systems, which is MUI. And then we start, when we talk about the zero carbon step code, we start looking at fuel choice. And that's when we start looking at greenhouse gas emissions in kilogram of CO2e or kilogram of CO2e per year. And then when we start adding embodied carbon, then we look at materials. And again, in kilogram of CO2e or kilogram of CO2e per square meter. And so important to understand that those metrics all will impact each other. And that's when we look at a home as a system, we look at each of those individual metrics, but they will be impacting each other. And so there are opportunities, and that's when the word optimizing comes in. There are opportunities to optimize a building instead of just maxing every single of those metrics. If I could give just one rule for designing better buildings, it would be this: airtightness before anything else. Why airtightness is so important is because anything else has diminishing returns. So airtightness doesn't, I mean, unless we go to the very, very, very low numbers. But unlike insulation or value, tightening a leaky envelope keeps paying off. So the lower you get, the better it gets. That's how it is. It also unlocks mechanical downsizing, maybe not the right word, but sizing mechanicals that are smaller. And that's where cost savings can happen. It's historically we've been installing very large mechanical systems to make up for that heat loss, but now in airtight, well-insulated buildings, we don't need such big mechanical systems, and so there are cost savings there. It also reduces moisture risk because moisture travels in the air, so leaky envelopes can cause rot and mold, and this is not happening in a very, very airtight envelope. This is also when we have airtight envelopes, and in the past you've heard that buildings need to breathe. It's important to have ventilation, absolutely, absolutely. And now in a controlled environment, this is happening with an HRV, and having an airtight envelope also allows your HRV, when commissioned properly, to operate efficiently. And when we start talking about embodied carbon, when we think about this, the airtightness can I'm losing my words, but airtightness can allow us to look at different metrics and optimize that building envelope. Meaning, and I'll show you a great example just next slide, but we don't need that many materials to achieve airtightness. And so the embodied carbon of lowering airtightness is actually low, as opposed to adding more materials, adding exterior insulation for extra, maxing out that TEDI metric. So I always start with this, because if we nail airtightness, then we've achieved a great deal already. And so I want to show you what happens when you get airtightness right. And so this is a home in US that we worked on very recently. And this is a home that needs to achieve step 5 and EL2 of the zero carbon step code. And we looked at, just for fun, if we could reduce the exterior insulation from 4 inches to 3 inches. And you have the list of the specs here. So quite a high performance envelope at 4 inches of exterior insulation with an airtightness of 1 ACH. It meets step 5. Now, can we reduce the exterior insulation by 1 inch? At 3 inches of exterior insulation with an airtightness of 1, no, the home doesn't meet step 5. However, if we were to lower that airtightness, keeping everything else the same, lower the airtightness to 0.6, then yes, the home can meet step 5 with 3 inches of exterior insulation. That is exactly the type of cost savings and optimizing that I'm talking about. Is the savings of reducing the exterior insulation are significant. Achieving 0.6 when you're already at 1 doesn't cost much more. It's craftsmanship, quality, making sure that everything is done right. And so this is the first example. Now, again, for fun, looked at what this home would look like if it were to meet step 4, EL4, which is the alternative in US. And so quite relaxed assemblies here and no exterior insulation. And so again, when we looked at airtightness, this home could meet step 4 with an airtightness of 1, but not an airtightness of 1.5, which is the required for step 4, right? So this makes the point that we can have lighter envelopes, and I'm not saying no insulation at all. This is again optimization. Lighter envelopes can achieve really great energy performance if the airtightness is really is really low and stress point. So this is exactly how we optimize the energy model on our end and what that looks like in real life. Now, the second strategy for thinking life cycle is don't spend more for less. This is the story of diminishing returns. So a few studies here show that once first walls are already well insulated, further increases typically deliver low or single-digit building energy savings. We've seen this, and I'll show you an example in a few slides. Passive house research shows that below 0.6 ACH, any further tightening has very little improvements again. So the big gains are between 3 ACH and 0.6 range. So I always say aim for 0.6. Anything below, fantastic, but 0.6 is really the sweet spot where it gets you all of those relaxations on other metrics. And the BCIT Building Science Group also showed that it's the same story for windows. So once you have good performing windows, you don't necessarily need the extra super well performing windows that cost more, because you have that same story of diminishing returns there. And we've also seen ourselves, and that's more of a field observation, not an official research, but we have seen that builders who try to max every single metric will have increased costs for about 10% of energy savings. So, and much higher embodied carbon. So we try to bring this philosophy to all of our projects to reduce the whole life cycle of buildings. This is a graph to explain the return and diminishing returns of insulation. So there's no clear-cut answer. I can't tell you use this much insulation in climate zone 4 and this much in climate zone 5. This is not how it works because, again, the energy model is there as a tool to help make those decisions. But there are multiple variables involved. We know climate zone is one of them, and the type of heating and cooling system, the fuel used for heating, utility costs, obviously, comfort, and then just the interests of the homeowners. But once you reach that R20, R22 wall, like you've already done great work. And so this is why, again, thinking back about the minimum code home that was lower life cycle carbon, because that energy performance and operational emissions is already really low. This is why, again, embodied carbon is a bigger part of the emissions now. Here, same story. This is a North Van project that we looked at recently, wanting to achieve step 4, EL4. And so we modeled what happens as you push insulation again from exterior insulation from 2 inches to 2.5, then 3. And so on the left side, you can see the heat loss from the walls, which shows, yes, pretty good numbers, but yes, in the low range. And then on the right side, this is the house annual energy consumptions. And here we are in the single digits, 0.58. We are like a less than a gigajoules difference. And so this is important in this conversation because the homeowners came to us, asked us, well, do we want to add 3 inches of exterior insulation? And after running those numbers, we looked at it and went, well, less than a gigajoule per year, that's really not much. That's less than $30 of utility bill savings over the entire year. So is it worth it? And here we are already with a home that is going to be comfortable, right? It is already achieving step 4. So the envelope is already really tight. And so here in this case, we're like, well, no, it doesn't really make sense. If there is one place that you can save on costs, it would be not adding that extra inch of insulation. And so we ran 3 models for that same house, same everything, and just changed the exterior mineral wool thickness. And from 2 inches to 2.5 to 3. And the bars here on the left show how much space heating you save each time you add another 0.5 inch of mineral wool. And it's about 131 kilowatt hour saved from 2 to 2.5. And then from 2.5 to 3 is about 58. So again, the number, the diminishing return is right there. The number inside the bar is what is important to pay attention to. It's the efficiency of each unit of insulation. So how hard is it actually working? And so we are getting like 3.5 less out of the same investment in insulation here. And this one is an important one when we talk about compliance because this home could achieve step 4 either way, right? So we are not even talking like, is this a breaking point for any of our compliance documents? It's not. This home is going to meet step 4 either way. And here's the reason why. So this is actually the heat loss breakdown from the Energuide report on the same house. And if you look at this and you see that windows are 30% of the heat loss. And so the walls and the conversation we were having was only about the walls. So when we look at this, then we were just looking at the wrong problem really for this house specifically is windows have 69% more, lose 69% more heat than the walls. So in this case, would it make sense for us to improve the windows? Yes. Over the walls? Yes, 100%. And then that's exactly what I talk about when I say optimizing, is when we look at those numbers, it helps us make decisions that are cost effective. All right. That's the last very technical slide, I promise. That's the conversation between step 4 versus step 5. So for this home, same home again. The current design is at step 4, EL4. What would it take to take it to step 5? And so the wall upgrades, air tightness would be the same wall upgrades, the teddy would need to be improved. And really here, the operational savings are very minimal. So 26 kilograms of CO2 per year of operational savings. However, the embodied carbon payback will be between 75 and 130 years. And so this is huge. And in this case, and that could be very different for a different home, different climate, different municipality. But in this case, the step 4 is the right call for this home. It is going to be a comfortable, energy efficient home that is going to use very little clean energy over the years. And so why adding the extra embodied carbon when you're already achieving really good comfort levels and performance at step 4? So this is not the case for every single home, but it is the case for this North Van home that we looked at. Now, talking about optimizing is also talking about making things less complicated. So we looked at optimization of insulation thickness, and I also want to talk about simple mechanical systems. So here we had a home, actually that was that same newest home where they wanted inflow radiant. And I know this is a topic that we get very, very often with homeowners. We want inflow radiant. I listed here what that decision actually meant in real life. So wanting inflow radiant, right? We need a boiler, gas boiler, better because cheaper. So we're going to install a gas boiler, but the gas boiler has too much greenhouse gas emissions to meet the zero carbon step code EL2. So the boiler alone doesn't work. So we're going to add an air source heat pump on it because that's going to help the model and compliance. Now that air source heat pump needs the cooling distribution. So now we are adding ducts. And then the ducts here didn't fit in the joist. So now we are going from 9.25 to 14 TGI to accommodate the insulation and the ducts in there. So, and then we are adding, in this case, a gas fireplace that adds just a third penetration into the building envelope. So this is quite, like, this was the decision-making process. Well, if we want inflow radiant, those are the things that need to happen for compliance. And this is quite complicated. In real life, on the left is what will get built. And that's quite a lot. Versus, they could have just installed an air source heat pump and the HRV, of course, but that's a much simpler system to install. First, you don't need 2 fuel sources and 2 connections. Like, there's just a lot less happening if you just install the heat pump. Now, I'm giving this very concrete example because we went through this very recently, and I'm not saying this is the case everywhere, but this is a perfect example of how simplifying mechanical systems will save capital costs and operational costs. And so the question about radiant floor heat, we've had it so many times now. And I agree that it's comfortable, but people who want radiant floor heat are people who have experienced the worst of housing. So in the past, there were single pane windows, no under insulation slab, no insulation under the slab, very leaky homes. So feeling that cold draft on the feet was very uncomfortable. And some are barely any insulation in the walls. So yes, of course, inflow radiant was the solution because you wanted to have those warm feet because you didn't feel comfortable. Now we are building step 4, step 5 homes. And so we have double, triple glazed windows. We have under slab insulation. The floor doesn't feel cold. We have no drafts and we have very well insulated walls. So you're not radiating heat anymore. The cold is pretty much gone. So you don't need that warm feet feeling unless in 100% in the bathroom. I am guilty of having those electric pads in my bathroom that I absolutely love. And yes, I would say if people want that warm feet feeling, yes, electric pads in the bathroom when you get out of the shower, this is fantastic. This is luxury. But the rest of the home is just an overcomplication of mechanical systems installed, build costs, and it's just adding more and more and more and increases. So after having looked at all of these, are energy efficient homes always better? Bringing back this question and now really diving into embodied carbon and life cycle thinking. So this is a graph about all of the life cycle stages that are calculated through a life cycle assessment. So really looking at embodied carbon. And so the production stage here in navy blue is where most embodied emissions happen. So often also called upfront embodied emissions. Use stage here is any repair, maintenance, and it's also going to be the use as well. So operational energy use is actually one little stage here, B6 only. And so the rest is anything from added materials, repair, maintenance. And then there is end of life stage. So end of life is anything that happens after the home has reached its end of life. So is it getting demolished? Is it getting deconstructed? What are we doing with the materials? Are they going to the landfill? Are they being recycled, reused? And all of those decisions have an impact in the end of life stage. So most embodied emissions happen upfront. That makes sense because, you're manufacturing and making a lot of new materials. And the other one that happens quite a lot is at the end of life stage because, yes, throwing everything away in the landfill has a lot of emissions associated with it. When I talked about optimizing buildings and started thinking about that life cycle approach, we have a project in Vancouver, a duplex that we looked at for those energy plus embodied carbon lens. And so we looked at, does it make sense to increase under slab insulation, have thicker walls, increase insulation on the walls, or again, airtightness, my point here again, and looking at the operational savings versus the embodied carbon. And so we went from about a 15 to 20 year CO2 payback to 35 on the embodied carbon here on the left for the scenario A, and then scenario C, which is if you improve your airtightness, again, extra tapes or extra membranes have much less embodied carbon. And so in this case, that was the best return on investment for carbon and costs. And that's the approach when we start looking at that life cycle thinking about what makes the most sense for this specific design. So what this means for people working in this industry? Well, first, airtightness. Can't stress it enough. If homes can all hit between 0.6 is really a great target. And that allows your energy advisor to optimize the energy model and be confident in those numbers. So if we can relax other metrics, knowing that we can achieve 0.6 airtightness, that's a win on costs, huge. Second, account for embodied carbon. I think the point has been made, but now I'm going to show you how to again account and reduce embodied carbon. Right size insulation is important. More is not always better. I'm not saying again no insulation. Saying all of the measures and policies that have led us here are fantastic. We wouldn't be here and we wouldn't have this conversation without that. Now we are just moving past that, thinking, what else? This was great. Now we have reached this point. How can we optimize for life cycle thinking and for embodied carbon? And then optimize, don't maximize. Sometimes the step 4 EL4 homes will beat a step 5 homes, depending on, again, the embodied carbon, the pros and cons, the balance there. So I'm a true believer, and I've said this for a long time, that a step 4 EL4 home overall will have lower life cycle carbon than a step 5 home. And this is not necessarily the case. And there are great research projects that show that you can achieve step 5 home and be very, very low carbon. 100% this exists. Now, in the current market, with the current materials and the current practices, it doesn't happen very often. So there are case studies of some homes, and it is possible, yes, when we start looking at bio-based materials, and we'll dive into this into the panel discussion. But realistically, what gets built right now on the ground is not there yet in terms of bio-based materials. So that's why this is true at the moment. Now, strategies to reduce embodied carbon. So first, it starts with building nothing. And I love saying this, and people look at me a little bit weird because, yes, we are in a housing crisis. We need to be building more housing, 100%. Building nothing here means relocating homes. So great example by Mariah, and renovating and deconstructing. So it's how can we do more with less? That's really building nothing. What building nothing means. Then there is building less, where we start talking about sufficiency, form factor, optimization. Then there's build clever, that's designed for disassembly and reuse. How can we make better practices down the road after the home is coming to its end of life? And then build efficiently, so minimizing the design loads, prefab, minimizing wastes. All of those strategies reduce embodied emissions and costs as well. And I'll give you some very concrete examples. I'm glad we have the same picture of that home being relocated onto the Sunshine Coast. Oh, this one, no, my bad. This one is actually the yellow house that went from West Vancouver, or Vancouver West to North Vancouver. But building nothing is examples are relocating homes. Great examples. This has been done by Nickel Bros for many years, and it is doable. It has some challenges, and I won't dive into this right now, but it's a number one strategy. Can the home that is there already can be relocated and reused as is with some energy retrofits done to it. Second point is renovate first. So upgrading the envelope most of the times, and again, based on approval of structural, but most of the times we can upgrade existing homes, upgrade their envelopes, their systems, airtightness, and make them perform as well, if not better, than some new homes. And Erica will be speaking about this and give us a great example here. And then if all of that is not possible, then deconstructing is the next best option. Deconstructing, why? Because we can reuse the lumber, and pictures here shown of reused lumber that was being used on a couple of our projects now, where lumber can be salvaged, and not just lumber, but a lot of other things in the home, and can be reused as well. So as of now, and we might want to talk about this in the panel, but wood cannot be reused in structural elements. However, there are people working towards making that happen. And in the meantime, we have worked on a home where it has been reused as part of prefab panels. And so this is a home in Burnaby, where reused lumber, so deconstructed lumber, was reused in prefab panels made out of Bowen Island. And we calculated the savings. I mean, that's a bit of a Frankenstein home, this one, because we reused as many materials as possible. Meaning, one day I got a call and it was like, "Well, we got wood fiber insulation from this site for free. Can we just use it?" I'm like, "Sure, we'll use it. We'll incorporate it in the model." And then there is this fiberglass as well that was available, and so we're gonna use fiberglass for this, and mineral wool. And so there's a bunch of things on this home, like everywhere, every little piece has used as much reclaimed materials as possible, which is fantastic. Challenging from a modeling perspective, because we had to account for that many percent of material was reused versus that many percent. Where did that come from? And quantifying the emissions associated with it. But fantastic project overall, reaching 109 of kilogram of CO2e per square meter for embodied carbon, which is well below about half what currently the benchmark is locally in the city of Vancouver. So great results, mostly coming from those reused materials. Overall, we quantified all of the savings coming from reclaimed and salvaged materials, and that accounted for about 6.5 tons of CO2e from all of the different materials that got reused from different sites, which is what is interesting. So on this site, reclaimed materials came from multiple deconstructed sites, which was even harder to quantify, but fantastic as a case study. And so overall, the point being, reusing and reclaiming materials can save quite a lot of greenhouse gas emissions. Next one up is building less. So building less, what we mean by building less is optimizing the form and reducing the material intensity. So here we talk about sufficiency, and the home that you see on the left here is a home that was built in Seychelles a few years ago, won the very first Embodied Carbon Awards. And in this home, we looked at the homeowners were very keen on just building what was necessary. Like, they want to overbuild. And they also wanted to build for future non-adaptability, but future thinking in terms of, well, if we need more space in the future, how can we make that happen? So on the left side here, there are plans that have already drawn an extra 2-story here on the left with an extra bedroom, a bigger living room. And so this has already been designed before this home got built, so that if the current homeowners or the future homeowners want to add space, it has already been designed for it, and structural has already approved it. So there will be minimal added materials here and construction work to make that happen, because it has been thought about already in the design. And so I have this other example, which is on West 20th in Vancouver, where this home was designed again to be turned, and I have better pictures of the foundation after, turned from a single family home to a duplex to a triplex with the foundation already there. So basically it would just be cutting a wall and opening it up, as opposed to demolishing the home and rebuilding, or completely doing like a full rehaul of the whole building. So really, building less is thinking about how can we reduce materials, right size spaces, think about the future, and optimizing any spans as well to that would require less structure elements, so less steel, less concrete, because those materials are very high carbon. That's the home that I was showing you on the left side. So it has been designed with also minimized concrete, and really thought about from a carbon perspective overall. We loved working on this project, and that was quite a few years ago already, but this is still current because it is very important to start minimizing high carbon concrete from projects. And this one was, the homeowner was very keen and was just leading this, and which was fantastic to see. And we don't see that very often. So very grateful to have worked on this project. Now moving on to this one on, actually this one is another one in Abbotsford. Again, on the topic of simplifying, right sizing and optimizing. This is a single family home with a street where the street has been designed so that it could be opened up here and into one big bedroom or two, depending on the use. Currently, they need 2 rooms here, but in the future, this wall here could be opened up with minimal disruption to the home, and minimal just work. And so this could be opened up, and it is a street here, and so this is also open here, so could make a big, large family home or 2 units as it is currently. And so it has been thought about in the design phase. So this is about optimizing, but also thinking about future use of the building. So that allows the home to remain in the family and also be passed on to other family members as well. Currently, nephews are living this space, and the grandma as well. So multi-generational living here. Another example of simplifying, right sizing, and optimizing, we looked at a home that was this time in Squamish, that was interested in doing an ICF crawl space with EPS insulation, and we're going to use Glavel. And yes, this is Glavel. It's not a typo. And we looked at different options and how we could reduce the impact overall of that crawl space. So this is quite a lot of modeling details here, but the point is we went from what's on the left here to what's on the right. And the decision here in Squamish with the soil condition to have a crawl space was actually quite high carbon. And so the homeowners decided to make it a vented wood space, and instead having just a wood ceiling and removing as much concrete as possible, so that the ceiling, the floor or ceiling would be wood based and therefore not concrete based. And so this removed also the EPS insulation under the slab, because now we were going to insulate that ceiling. So with lower carbon insulation materials. So again, type of conversations that we can have in design about optimizing for carbon. In this case, they went with the option on the right here. Now, a couple examples on building clever and designing for reuse and adaptability. That's a home actually called Adapt in Vancouver. Erica and I got to tour it last year. It is now fully built, and I passed by last week, and it looks exactly like the picture. That's the house where I was mentioning. They actually, better picture on the next one. It can be adapted from a triplex to a duplex to a single family home. So currently it is a single family home, but the plans have been made so that it could be changed to a duplex or a triplex. And so this is how it looks like currently. But then you see like the walls were made in a way that you would need to just open it up, and that would create space for the duplex or the triplex. And that all started in the foundation. And so that's how it looked like, just the way it was built, in a way that you would just need to really open it up or close it off. And here you have multiple units, and you have doors on the side that were also allowed in this case. And just so in the future it can be adapted. And we can come back to this later as well. Just mindful of time. Building efficiently, here we look at minimizing design loads, prefab, and minimizing waste. Prefab, a great way to minimizing waste, as well as choosing low carbon materials. So those are examples. Those of you who know me know that I'm a big fan of wood fiber insulation. I don't know if we want to get into this right now, but there are a lot of lower carbon materials available. And this is part of this strategy. And so low carbon materials. First, we'll talk about concrete, and in the panel, we'll really dive into this. So very glad to be speaking about this after this presentation. This is coming from a guide that the city of Nelson commissioned for Nelson, looking at different concrete mixes and their embodied carbon. I love this guide because it's very visual, and you can see really clearly which ones are lower carbon than others. But concrete is always the highest carbon material on all of the projects, just coming from cement and manufacturing of cement. So anywhere that we can either reduce the amount of concrete or use lower carbon concrete, it is a huge win. And so we'll dive into some of those strategies in the panel discussion here. Next one up is usually installation, and where decisions can have a big impact as well. So same in the same guide here, same principles. It looks the same. If we can stay away from the top emitting materials again and move down the list, that's the way to go. So we can build step 5 homes with straw bale, and we have a good example of this in the panel. But we can also, for some people, it is a big jump to go from up here to up here, right? In terms of practices, in terms of crews that are not used to the materials, the techniques, etc., etc. So I always say, if we can avoid the worst of the worst and then move your way down slowly, then that is already a win. And so I have examples here of a Phoenix House, a project who that also won the Embodied Carbon Awards, which we use dense packed cellulose. Cellulose is fairly cheap as an insulation material, and so works really well. So those are dense packed cellulose walls. And we also used in that same home hemp bats in the interior walls. At the time, couldn't use hemp bats in the exterior because they weren't certified for it, but I believe now they are. And the hemp was used here on all of the interior walls. And I can't tell you, just looking at the picture, the smell of this when you entered at mid construction, it just smelled natural. It didn't smell anything chemicals. It was just it felt like entering a field. It was just really nice. And that's also part of the benefits and co-benefits of using bio-based materials, other than their obviously low embodied carbon, is they are natural materials. So the crews installing them are not, in contact with any harsh chemicals or anything. Like, this doesn't get itchy. This is a really, really great material. So insulation is usually an easy swap for projects to go from high carbon materials to low carbon materials, which is why I listed here. We have also on this home had the conversation about asphalt versus steel roof, which is always a topic, because if you look at only the upfront carbon, the asphalt is a little bit lower than steel, but really steel, you can keep it much longer than asphalt. So what is the right decision? It really depends on the objectives and the goals here for the project. But we had this conversation for this home, and the homeowners were very, very keen on going the lowest carbon approach. But in the case of asphalt versus steel, well, what is the lowest, right? Like, do you want to have upfront lower and replace your roof every 15 years? Or do you want to have a longer lasting roof that might be a little higher on the upfront? And so at the end of the day, the architect found a really great material called Enviro Shake, which is 95% recycled tiles that look like I should have a picture. They look like tiled roof, but 95% recycled material, and they have a 50-year warranty, meaning that it will outlast everything else on the market. And so when thinking about that life cycle again, this is probably the lowest carbon option, and also the most durable, meaning less maintenance, and the homeowners won't have to deal with their roof for quite a long time. So how life cycle assessment can become a tool in the decision-making process, those are some of the examples that we've worked with. And I'll end this by mentioning that there are two major resources. So I mentioned in this slide, the City of Nelson has the Updated Materials Guide of 2026, fantastic guide. And then the Carbon Leadership Forum also has a low carbon materials sourcing guide, where you can find low carbon materials that have been vetted by a group of volunteers. Full disclosure, I'm one of them. I actually worked on the cladding materials for this guide, and they are listed by highest carbon to lowest carbon. They are locally available, and there is the contact for the sales rep or the website for reaching out for procurement. So this is the end of my presentation. I know I covered a lot. If you have any questions, we'll take some questions now before we dive into the panel discussion. But I'm also on the most technical slides that I passed over quickly. I'm very happy to answer any questions over email after as well. So just dropping my contact here.
Thanks, Elizabeth. That was fantastic. We don't have too much time, but we do have one question in the chat that we can answer for now, and then perhaps any other questions we can answer after the panel. So Matt is asking, regarding the insulation values given, right sizing to R22 to R30, and the earlier slide on adding insulation to uninsulated homes, is that nominal R value of the bat insulation used, or effective R value of the assembly?
Nominal R value.
There is a second question, so let's just dive into that one. We have 1 minute here. Have the low carbon materials been vetted with respect to the BC Building Code compliance criteria, i.e. material standards and/or fire safety, or only in a low carbon context?
Great question. I want to say mostly from the low carbon context. However, yes, because some of those materials might need, and maybe Erica, you can speak to that, they might need special approval process. However, you would be able to use them in Canada. So it is in the, Erica, please help me here.
So one of the things that I come up against sometimes, most of my work is on the North Shore, and we have the fire restricted zones where you have to choose non-combustible materials. So sometimes that means even I question whether or not wood fiber insulation would meet that criteria. They do have fire testing data, but I haven't had the opportunity yet. So far, up until very recently, I think it was January of this year, there's one company now in the Lower Mainland. Are they online yet, Elizabeth? Producing?
No, not yet.
Okay, so they are not yet online. So right now, our only source for wood fiber insulation is overseas, Gutex out of Germany. And it's about 2 to 3 times more expensive than mineral wool. So mineral wool has the advantage of being fireproof. It comes from rock slag, and so it can be used in these fire zones. So as far as like what I see putting building permits through building departments, if they have fire restrictions, they're going to go with what they're comfortable with. And because the local jurisdiction has approving authority, then the building code itself hasn't necessarily vetted certain materials, but the authority, based on negotiations and dialogue, if you can convince an inspector or an approving person in their planning building department that yes, this material has all of this data, and you show it with the proven test data under the standards that are appropriate, then you might get it accepted. But it's really up to the local jurisdiction because they're the ones that have put this overlay of the development permit guidelines.
Thank you, Erica.
Thanks, Erica, for jumping in there. We are going to have to move on, but feel free to put questions in the chat, and we'll see if we have time at the end of the panel to go through them. Thank you again, Elisabeth. That was a fantastic and insightful presentation. So at this point, we're going to transition from the presentation into our panel discussion, where we'll explore how material selection decisions play out in practice across different roles and regions. Today's discussion will focus on how teams are balancing cost, performance, and carbon when selecting materials, and what's actually working in terms of real projects. So we'll start with a quick round of introductions from our panelists. If you can share your name, role, region, and the types of projects you typically work on. Elisabeth, let's start with you, and you can reintroduce yourself and share anything else you'd like to. And then we'll go to Mike, Erica, and then Dan.
All right, Elisabeth, founder of CarbonWise. We are energy advisors and lifecycle consultants. And as you can see, we like to nerd out on anything materials, energy, carbon, modeling, and love. I'm very excited about this conversation and to hear from Mike, Dan, and Erica here.
Hello, everyone. Mike Coen. Yeah, I wear many hats. I'm builder of a Step 5 near zero embodied carbon laneway house. And I also sat on the panel for the City of Nelson Low Carbon Homes Pilot. I'm currently a building official inspector for the City of Nelson. And yeah, long-time builder and embodied carbon enthusiast. And I'm just happy to be here.
I'm Erica Wolowidnyk. I started EW Architecture a number of years ago. My focus probably for the last 10 years has been continually educating myself on sustainability, including embodied carbon, zero carbon, all of that. And the sectors of work, I do a lot of single family residential, but I also do institutional, commercial, and like Part 3, Part 9 buildings. And always looking to encourage and educate my clients to make smart choices related to buildings, whether it is reducing or renovating to reduce that landfill waste, and thinking about your fossil fuel choice and using then the materials that have hopefully lower embodied carbon. And in our community, because costs are such a big driver, sometimes you have to make trade-offs, and cost and availability also affect those choices.
I'm a supplier of ICF and MST rebar, fiberglass rebar. We have a traditional farm rental company, but we're also a contractor company for flat work, including residential, commercial, and municipal, sidewalks, curbs, things like that. So those are the spectrums that we cover.
So let's start broad and ground this conversation in what you'll all be seeing in your work right now. What key considerations should teams include when approaching material selection, especially when balancing cost, performance, and carbon? Dan, can we start with you?
Yeah, sure. I mean, it's a bit unique with the concrete because a lot of the low carbon, if you reduce your MPA, you're saving money. You're getting cheaper concrete. And somebody in the industry, I see all the time people using way too high strength of concrete for the purpose of what they're doing, and also using way too much volume. There's a lot of areas that can be reduced. So aside from using high fly ash mixes and low carbon concrete, I think even more importantly is understanding mix designs, the strength that's needed, and the whole going stronger is always better. Not really. Yeah.
Thanks, Dan. Erica, your thoughts?
So on material choices, I'm trying to look at the embodied carbon as well. One example is the insulation question, very much against spray foam for a number of reasons. It encapsulates everything. It turns the entire building into garbage. And so you can never really recycle that home. So spray foam is bad for that reason, and also because the catalysts are have a very, particularly on the closed cell, have very offensive emissions for the environment, and then also the health impacts for the building occupants. So, and that even with the open cell, the primers they use to create an air barrier or a vapor barrier are toxic. So it's very much a health issue. And then also looking at things like performance. An example of the West Van house that we did, it's complete renovation. We wanted to look at insulating the basement, so we created our own ICF, and the insulation choice was GPS, the graphite infused insulation. It has almost the same performance. It's a 4.7 RSI versus a 5 RSI of XPS, but it's basically EPS with graphite infused, and the graphite beads help it's not just the conductive properties, it's the little beads of graphite reflect the heat. And so it performs at a much higher level. It has lower embodied carbon, and overall it costs about half the price. So looking at all of those factors, and I could talk about all the other materials as well, but I only have limited time, so I'll just use that one example. We try to look at all the factors: cost, embodied emissions, functionality, health.
Thanks, Erica. That's great. I'm really glad you brought up the health side of things. Thanks for that. Mike, how about you?
Yeah, well, it's really a balancing act. We're trying to meet performance requirements, embodied carbon, project budgets, health requirements. And especially when it comes to step code, we need to be choosing materials that are going to, enable us to meet those step code requirements. One thing I would push is education. So, if folks are out there and they're designing or looking at building, then, jumping onto the City of Nelson's material impact guide and looking through those different building components and seeing where they fall on a scale of embodied carbon and performance and cost. That's a really good guide because it does lay out all those areas. Yeah, and there's tools out there like the Beam tool, if folks really want to take a deep dive on it. But yeah, it's a balancing act for sure.
Thanks, Mike. Elisabeth, over to you.
Yeah, I think some of the examples I gave here were where we had the best results, and I agree in terms of thinking about health as well, and thinking about the long term and durability of those materials. So, the roof one is the one that I quite enjoy talking about because we there is the upfront carbon, but there is the maintenance and the replacement, etc. And the end of life, right? So, for example, if we think only upfront carbon, then asphalt looks better on the numbers. But we have to think about the practicality as well. And so we had clients in North Van that wanted to install solar panels, and they were debating the steel versus asphalt conversation. And at the end of the day, decided to go with asphalt because they will be changing their solar panels in maybe 20 years. And so at that time, they would basically take the whole roof down and replace the whole roof system. And so that's how it happens in real life, is that we are there to model options and provide options. And obviously have very strong feelings towards wood fiber insulation in a good way. But it's also not always feasible, like Erica mentioned. So it's about balancing all of those key elements. But some of our projects that have achieved the best embodied carbon performance were all about the strategies that I showed about reducing the amount of concrete, optimizing design, having a lean design, and then using dense packed cellulose. I mean, we've used it on a couple projects now. It's a great material. It achieves really, really great thermal performance. And on this one, we achieved 0.28 air tightness. So extremely great on that project. And looking at windows as well is always a conversation, double versus triple. Which one is better, right, from an embodied carbon performance? And I wish there was a clear-cut answer again, but not always. And we've decided to go with some mass timber windows that were coming out of Europe, but that were actually lower carbon than some of the ones that we see locally. So again, it's the pros and cons on each of those materials, and managing the budget obviously is extremely important. And moving the items on the budget, right? So if you use a little bit more, maybe for that EnviroShake roof, which was, I think, 25% more, but you're also going to be using a little bit less on your insulation here because of the cellulose. And then you're going to need very small mechanical systems as well, so that it's balancing the budget this way. And again, optimizing. I love this word.
Thanks, Elizabeth. I've seen a lot of Energuide reports over the years, and I don't know if I've ever seen an ACH as low as 0.28, so that's fantastic. For all of you, how are supply chain challenges like availability, cost volatility, tariffs impacting your material choices? And what's helping you manage those constraints in practice? Erica, can we start with you this time?
Again, I'm going to refer to that West Van house. We did choose mineral wool exterior insulation for the walls and the roof, and found that this was a few years ago. There were supply chain issues. You know, rock wool is the go-to supplier that people always think of just because the name is so catchy, and they've been around a long time. But we couldn't get the material, and the builder actually did some digging around and found a local supplier that had it. And so we were able to switch suppliers and get it. I'm not personally involved with those challenges because I'm on the design architecture side, but you know, working with great contractors who can be resourceful is kind of how we have to approach them.
Great, thank you. Dan. Oh, Dan, you're muted again.
Okay, sir. I'll get the hang of it. All our we're not affected by tariffs at all because of our everything we do is made in Canada. Everything we supply, but the cost of fuel, all these temporary surcharges are starting to really add up for us. And I think it doesn't really matter in material choice. Everybody's being hit with the same thing, but what it is doing is just reducing people's desire to build. So I don't think it affects our products over anybody else's product. I think it's across the board, but it's definitely slowing down the building.
Yeah, I believe that. And I'm glad that you shared that. It is across the board and not one company is experiencing it. Elizabeth.
Sorry, I had to step out just to grab a glass of water. So I reached this road this morning. Remind me, budget and how do we manage availability?
Yes, exactly. How are supply chain challenges like availability, cost volatility, tariffs affecting basically your work?
Yes, well, I think there is, on the topic of tariffs, a great opportunity to use more Canadian-made materials. A lot of the lower carbon options are actually made in Canada. We manufacture some of the lowest carbon steel and concrete in Canada. And there are great opportunities for purchasing lower carbon alternatives made here, especially in BC too. And on the supply, we've also used for the hemp bats, that was a company out of the East Coast. So also trying to buy local. When we again look at the whole life cycle, what I found interesting is sometimes a material can come from further out, but if it comes on rail, that would actually be a lower carbon option. So it's again managing and looking at the numbers and asking the right questions to suppliers is how we make those decisions at the end of the day.
Great, thanks, Elizabeth. And Mike, round us out.
Yeah, I guess pre-planning plays a big role, and depending on the material choice, we've been talking a lot about conventional materials. How about the discussion of unconventional materials? Your straws and your hemp, crete, things like that. So if that's the area you're trying to go down, being more bio-based and unconventional, then making sure these products available at design phase, and the more local the better. If you can get straw from a farm that's within half an hour or an hour away, that's a lot better than importing it from Alberta or something like that. Like Elizabeth said, keeping it local is key. Saving on tariffs and things like that, and then planning and being sure that material is available.
Thanks, Mike. Yeah, it's really interesting to hear about these more so unconventional options and definitely leaves some room for creativity, I would say. How do you folks approach conversations around material selection, whether it be for increased energy efficiency or lower emissions? And Mike, maybe I'll just go right back to you with that question.
Yeah, sure. Well, yeah, it's another balancing act, meeting energy efficiency requirements with step code, trying to balance embodied emissions. So yeah, we can go back to the unconventional bio-based materials. If folks are going down that path, then they need to be aware that registered professionals will need to be involved in the project to help meet code compliance and step code compliance. And then if folks are using conventional materials, resources like the BEAM tool calculator and the City of Nelson's material impact guide will kind of, you can take a certain material from two different manufacturers even, and one manufacturer is sky high in embodied carbon and the other one is quite lower depending on the energy source for that manufacturing facility. So yeah, education there on, you can build a totally conventional home with regular insulation, fiberglass, or drywall, EPS foams, but just choosing the manufacturer that's readily available can drastically reduce your embodied carbon impact. So yeah, just taking the time to get to know the products and doing a little research into it is huge, really.
Thanks, Mike. Elizabeth.
Yeah, I'll echo what Mike said. Taking the time is on our Phoenix House project. What it has all been about, really, like outside of the modeling and agreed the BEAM tool, is what we used at the very beginning to find those hotspots, and then focusing on those, top 3 materials is where you're gonna get the best results, like the faster result, right? Like if you focus on the top 3 materials, then you can reduce your embodied carbon quite a lot by making those simple decisions. And then moving on to like procurement later after, like I kept receiving calls from the builder and the homeowner on like, well, can we use this, Elisabeth? Like, is this gonna impact our carbon numbers? And it went way beyond just the structure and the envelope, which was part of the life cycle assessment in this case, but it was like they wanted a bathtub that also was low carbon and sustainable and made in Canada. And so I was part of those conversations. And when modeling is one thing, right? It's helpful in making those decisions, but it also is looking and spending the time to look at the materials, because there is no information on this bathtub, right? Like, how do I know if it's a good or a bad option, right? So they can make whatever claims they want unless they have an environmental project declaration, but they didn't in this case. And so I spent the time to meet with them, and first time that I got to see like and understand how a bathtub was made of, and really understand that process. But again, spending the time is what makes this successful. So because otherwise you would go with what is just visible there or on the shelf, and that's not always maybe the best option.
Thanks, Elizabeth. Yeah, taking that time, doing the research, it pays off and it's worthwhile. And it will probably help you on future projects as well. Let's go to Dan next.
Okay, got it. Uh, well, I would say my biggest, we've tried to educate contractors and everybody on using low carbon products like our fiberglass rebar and like our using mixed designs that are low carbon. That's great, and you can get people excited about it. But if it's not in the design or thought about out of the gate and right out of the start, it's almost impossible to change gears. A lot of times, even we show up to our pours and we ask, can we use this mixed design or that mixed design? The general contractor doesn't want to go through the trouble of contacting the engineer or the designer, whoever it was. I mean, it would be a lot better if the mixed designs were performative and not prescriptive, because then it would give the batch plants the ability to adjust it, at that time. But too often, it's already too late as far as everybody's concerned. So I think the biggest thing that I'm finding is I've got to get all this stuff in at the design stage, because there's no time later. Even though sometimes it's a much cheaper option, people aren't willing to change gears when you're under the gun on a project. So it's all about getting all these things sorted out at the very start with the design.
Thanks, Dan. And yeah, that kind of tends to what Elizabeth was saying too. Just take that time. Don't rush the project. Don't feel like you need to jump in immediately. Erica.
I'll just comment quickly on one thing, Dan, is perhaps connecting with structural engineers and architects would be a good thing. One of my other hats is I have a California license, and for many years now I've had to do zero carbon courses. And I took a very good course on low carbon concrete, in which there's a plant in California who actually installed a wind farm to produce the energy to produce their concrete. And through that, because the cement extraction, or, burning the cement or whatever that is, that to create the cement, or burning the limestone to create cement, requires so much energy, that's where the carbon is. So since now they're using renewable energy, they've been able to lower their embodied carbon numbers significantly. That's not something everybody can afford to do, but I can connect you later with this resource, and it may be professionally someone you want to talk to about what they're doing versus what you're doing, and grow your firm that way.
Yeah, that's good. And to your point, in terms of learning with our fiberglass rebar, I learned that lesson about starting at the bottom. So we had a seminar for all the local engineers and brought in the experts to talk about it, to get everybody comfortable with it. Again, that's where I realized I have to start.
Yeah. So to talk quickly about the question, I would say, going back to one of Elizabeth's points of build less, In my practice, I'd say at least 90%, if not more, of my projects are renovations. And that's where even if someone comes to me and says, I want to tear this down and do a new one, I say to them, let's look at what you have first. I've done absolute transformations where somebody has no idea it's a renovation. And we've saved the embodied carbon of the slab, most of the foundation, the framing. Those are the most significant parts. And then they can get a brand new looking house. We've also approached insulation in such a way where we actually eliminated cavity insulation and vapor barrier to save costs and put everything entirely outside, which also in these older homes improves the health of the building, because wood that's been exposed to very poor air tightness has always been stable, warm, and dry. And now all of a sudden, if you pack that wall with insulation, you put a vapor barrier on the inside, across the profile of that lumber, you're getting both thermal and moisture stresses. And so that now that its intention, it's like straining just in its position that it's never done before. So moving that entirely outside improves the wood health and the health of the overall building. So it's thinking, like I said before, overall building health, cost, budget, occupant health, it's all interconnected, and it's that holistic approach that was at the beginning of Elisabeth's presentation.
Thanks, Erica. I really appreciate that. So let's bring this conversation into a specific project example. Erica, thinking about your deep energy retrofit project in West Vancouver,
Yeah.
what material selection strategies were most critical to achieving that high performance?
I feel like I've kind of touched on this question quite a bit already, but generally, I would say the exterior insulation approach was key. And what that let us do was shift the dew point and get our air tightness to be very good. We went from the 1929 deep energy retrofit. We stripped it down to the bones. We went from 14 air changes per hour down to, I think it was 1.1. Initially, they said we met step 5, but technically we met step 4. And this was completely voluntary. So doing renovations, you're not required to do step code, but it was the client's vision. And of course, I'm along right in there with them. And so air tightness was key, and then keeping the budget in mind, but it also provided amazing design opportunities. We exposed all of the existing framing of the roof. So on the upper floor, you look up and you see this ceiling painted white with all the framing lumber, and people are so intrigued by that. It's just, like, oh, what, this is the original 1920s lumber that's in this house, and they saved it. Anyway, that's kind of like the materials were sort of like all related like that. I don't know what else to say.
That's great, Erica. Natasha also just threw into the chat a link to learn a little bit more about this project.
Oh, one other very important thing. We completely eliminated gas. And that was what did the most on our carbon footprint. So the GHG emissions before, I'm forgetting, I think it was 10.1 tons of carbon a year, and we got it down to 0.1. And gas was, I have another one that's a separate house that we didn't improve the envelope because it was only, the house was built in 2006. So it was just simply, the entire project was about eliminating gas. And in that one, we went from air changes of 6 point something down to 2.8, just by tightening up the envelope with, putting inserts in the fireplace that could be removed when you actually use it, and going from a regular dryer to a heat pump dryer. It's inflow radiant heat. So we got rid of the gas boiler and installed an air to water heat pump. And so to Elisabeth's point from the sides, it can be done with a heat pump. It's an air to water heat pump. Yes, it's more expensive than an air to air heat pump, but if you care about the environment, it is possible, and I have proof of that. Induction cooktop, got rid of gas. So our overall emissions went from 6 something tons down again to 0.2. And this is in a standard construction 2x6 fiberglass bat. It's not the high density R24. It's just the regular fiberglass bat that was available in 2006. Poly, which I'm not doing anymore. I'm doing smart vapor barriers now. And so it was standard construction. And then we put solar on the roof, and our energy report says we're net zero. So that's data I'd love to share with you, Mariah. I'm still collecting. I want a year of BC Hydro bills to see, are we truly net zero, or is that kind of just a little bit of fiction there?
Incredible. Yeah. Thanks for sharing more on those numbers, Erica. That's amazing. And again, I urge people to take a closer look at the project in the link that Natasha shared in the chat. We could probably have a whole webinar just on that project. Let's see. I just lost my place here. So let's shift into newer or less conventional materials, as mentioned earlier. Mike, you've had a bit of experience on projects that utilize unconventional building materials, such as straw. In projects like this, what approaches have helped you manage cost, risk, and constructability?
Yeah, I'm going to speak to a project that was a light clay straw project. It wasn't built by me. It was built by a local builder here in the Nelson Kootenay area, Alexi St. John Duncan of Kaolin Design and Build. And I was part of a case study that the City of Nelson performed for this building. And it's a great example of a step 5 high performance, non-conventional, low carbon, bio-based, healthy home. And it's basically, the link will go in for folks at home. It's a 2x4 wall, split stud, so 14 inches. And what Alexi did was he used a chopped light clay straw mix, and he built forms around these walls. And he stuffed the straw in to build these thick walls, and then once they were to the ceiling or to the underside of the trusses, they were finished with like a clay plaster. So it was conventional building, foundation, slab on grade, and then the 2x4 stud walls, single story, and then a big truss roof. And it was an awesome build. And labor intensive is one thing we'll say, but the thing Alexi was explaining is that the labor was it was non-skilled. So it was a community event. When it came time, once the house was framed, it came time to build the forms and do the straw and the unconventional type stuff. It was a community, community event. People came to help, friends, family, even the engineer on the project came and lent his hand for a day just to learn a little more. So yeah, that was just a really good example of a non-code compliant, in a sense, still meeting step 5, high performance, healthy, beautiful home. And I spoke to Alexi yesterday actually just to get an update, and he's living in it, and he couldn't be happier. It's just a really comfortable house to live in.
Really cool. Thanks, Mike.
For sure.
Just a side question. Are you starting to see these materials getting used more?
I wish to say yes, for sure. From a building official's perspective for the City of Nelson, I haven't seen one be proposed yet. But if anyone out there is a builder locally, we're open to working with you guys if you're wanting to build out of these non-conventional materials. Yeah, generally, because it's doesn't fall under Part 9 or doesn't conform to the building code, so to speak, we will work with you on trying to make that happen. Generally, we'll need an architect or a building envelope consultant and a structural engineer. But that's kind of the main hurdle to get through, and then yeah, they perform the sign off and at the end. But yeah,
Really?
Not as many as I'd like to see, put it that way.
Maybe it's our future.
Hopefully, yeah.
Awesome.
Yeah, for sure.
From there, let's zoom in on one material that has a big impact, which is concrete. Dan, from your experience advocating for low carbon concrete in the Kootenays, what are the most effective strategies to reduce embodied carbon in concrete while keeping projects practical for contractors?
Yeah, well, as I mentioned before, I mean, from a practical and cost perspective, it's just reducing the use of concrete and reducing the MPA of concrete, because both those reduce the cost. So it's sort of a win-win. But also using, in our case, it's a fly. You either replace cement and concrete to make it more environmentally friendly. You replace it with fly ash or with slag. In our area, we use fly ash. And we can increase, typically what they were using here was a 20% fly ash mix. We can easily use 40%, and we try and encourage people to use it. Again, it's back to that design issue. A lot of times it's too late, even on our projects. When we show up and ask, we can't get the permission to change. Again, if the designs were performative instead of prescriptive, we could get around that. That wouldn't affect us at that stage, because then it's up to the batch plant. One question I get asked a lot is, well, this is a short-term solution because fly ash is going to run out. I did check into that, and it's right now it's about a 15-year supply, because fly ash is basically the result of the waste from burning coal, and it's just been stockpiled, and they're basically digging it back up out of the ground and using it now. But we are gonna run out in about 15 years. Apparently, they have an awful lot of it in China, but then that's another carbon footprint issue: is how do you get it here? So it's like fix one problem, cause another. Yeah, and so I think the number one thing is, I think also I'm a big proponent, and wasn't happening around here, is recycling concrete. People weren't recycling it. And we're lucky in our area, we have a guy that takes it and recycles it for free. You don't have to pay to get rid of it. So, and concrete with rebar, and it doesn't matter. It can be broken down and reused as gravel. So if we look at the whole life cycle of concrete, we should be taking that in consideration. And I know most people in this area were just dumping their concrete rather than turning it back into a usable product. And put pressure on your local on the local suppliers, your concrete ready mix suppliers, because even in the remoter areas where they don't have silos for fly ash, or they don't have slag, there's new chemicals. There's stuff coming out all the time for concrete. There's new chemicals that are strength enhancers, that you can reduce your cement content by adding strength enhancers, and you don't need expensive silos and things for that in your mix plants. So there's a lot of technology that's not being used that could easily be implemented.
Amazing. Thanks, Dan. Really interesting and great to hear that in your region there is that organization doing that recycling for free. And I think across the board, recycling is definitely, like, it's a big gap that's missing just within the industry. So thank you. Okay, to slowly wrap up the panel, let's focus on practical takeaways. So, question open to everyone. What's one specific action someone can take on their next project to reduce embodied carbon without adding a significant cost or complexity? And I'll just add at the same time, are there any existing resources that you can also recommend? Elisabeth, let's start with you.
Sounds great. I would say involve again that integrated design process that we've been talking about for energy for so many years. It applies to carbon. Just start the conversation early. The earlier the better. The earlier the better, because if we bring in this topic, and on the Phoenix House project that we've worked on, I got involved and sat down with the homeowners, the builder, even the site super, and the architect before the walls were even drawn. And we were just brainstorming and thinking, like, what are we going to do from an energy perspective, and then what are we going to do in terms of a carbon perspective, and bringing that conversation early. And the more I was speaking, the homeowners were very interested. So it's not often that we get involved with the homeowners, but I always advocate for teams getting together, even if it's just the builder, the architect, and the energy advisor and mechanical early on. This will save a lot of headaches down the road, but it also is the opportunity to think about, well, have you done this before? Yes, no, do you think that's doable? And especially when we think about unconventional materials, right? Some of it, like Mike mentioned, it requires a new technique, right? So in this case, is the builder on board with that? Because if for us, we recommend it and the builder's not able to build it, or it adds complexity, it will add costs, it will add time. And in this case, then it's not practical, right? So in order to keep things practical and cost effective, they need to be discussed very, very early on. And of course, like shameless plug, but yeah, doing the modeling very early is going to be where we can look at what's the most effective thing to do. As I was showing in some of the slides with the return on investment, the diminishing returns, this is done through modeling. So modeling is a tool. It doesn't replace everything, but it is a tool to help in that decision-making process. Start working on the top materials, start working on what matters most, as opposed to maybe one little detail that you thought was important, but the modeling was showing that it's actually not that important into meeting your energy and carbon metrics.
Thanks, Elizabeth. Dan, let's hear your thoughts.
Sorry. Well, I guess, I mean, I think the number one thing that I'd like to see is, well, I think I've covered so much of this in design and everything. The biggest thing that I've lately sunk my teeth into is fiberglass rebar, which, you know, depending on where you go, it's from 50 to 75% reduction in carbon footprint in use with the concrete. And it's longer life and better performing. So, and currently now the same cost. Cost was always the restriction before. So if we could use low carbon mixes, reduce our volume, recycle what we're taking out, and use fiberglass instead of steel rebar, I think I always laugh. We're the biggest offenders, you know, when I in the carbon committees and things, I'm sort of the biggest offender because I have the biggest carbon footprint. But as it was pointed out to me, we can make the biggest difference by making some small changes.
Can I please ask a quick follow-up question for Dan here? Like you mentioned the performance versus prescriptive in the design. Like what would that look like in practice? Like what would be ideal for you to receive as the manufacturer?
Well, so I'm not the manufacturer, and this is in conversations that I've had with our local suppliers. You know, they get a mixed design on their drawing that specifies exactly. And I mean, there are tons of concrete designs. It's endless. But they get a mixed design. Whereas I know our local supplier, if you told them this is what I want to achieve, and they can come up with a better design for that fact. It's not a cut and paste from over here to a drawing that we now have to adhere to. It's this is what we're trying to achieve, and let's go for that. And oftentimes, and especially if you've got ready mix suppliers that are keen on this, which we're fortunate, we've had some good movement in that direction here locally. Then they'd be willing to work with you and give you a design that actually does the job without getting way over the top on our cement contents.
Can I add a comment to that?
Yeah.
I see all the time, whether it's you know, in the design field or in the engineering world, it's that, oh, we did this on our last project, so let's just use that philosophy. But I just had a conversation with contractor yesterday. I said, can you please have your plumber review my plumbing schedule? I'm picking this based on specs. He's working with this stuff every single day. He's going to have an opinion. I want to hear it, because you guys and your suppliers, they're doing concrete every single day. They're constantly trying to make improvements, and the engineering community can't possibly keep up with those advancements. So if you had that opportunity to give your input and say, hey, this mix, it meets your strength criteria, it meets all these other criteria you've set, but it's a better mix and it's got a better carbon footprint, and we use it. It's just that dialogue and that opportunity and getting the awareness out to the community of engineers that needs to happen, I think.
Yeah. If I take out my contractor hat and my supplier hat, it was an uphill struggle to get guys to stop using 8-inch ICF where they didn't need it and go to 6-inch. It's like, no, we always did 8 traditionally.
This is the way I've always done it.
Yeah, it's the way I've always done it. And then, you actually only need 20 MPa for ICF walls, and most contractors ask for 30. I mean, that's 100 extra kilograms of CO2 per meter. It's just it's crazy, and they think that they're being better builders by. That's the problem. That's always the oh, I build better, I build stronger. Well, at a certain point, just like you were talking about return on insulation, you're not gaining anything by it. You're just putting a lot more carbon in the atmosphere.
Thanks, Dan. Mike, over to you for final thoughts.
For sure. Getting in early in design is key. Reduce the high emitters, your spray foams, your concrete design. We've gone over concrete a lot, but it's super important. And during that phase, hire someone like Elisabeth, get her on the project, really, that'll make a huge difference. And then beyond that, the most important thing would be material substitution. Download the beam tool and, go through every material, every product on the project and choose the one that's locally available and has the lowest embodied carbon footprint. It's pretty easy thing to do. And yeah, that's the low hanging fruit. And then what else was I going to say? Resources. The City of Nelson have just updated their material impact guide. I'm not sure if that's gone into the chat yet, but that's a super valuable resource, and it really breaks down embodied carbon, performance, cost, and all into one easy to read guide. So shout out to Alex and the City of Nelson Low Carbon Homes Pilot for that one. And Builders for Climate Action. Grab the beam tool, play around. You'll learn a lot.
Thanks, Mike. And I think Elisabeth threw a link to the beam tool in the chat as well. And just to round us up before we move into the Q&A, Erica, any last thoughts to add?
Yeah, I guess I would stress more and more renovate first. That's going to have your biggest impact on carbon reductions. And when it comes, a lot of people are terrified of renovations. They say, oh, it's going to cost more. It's more complicated. Yes, it's more complicated, but it doesn't need to cost more. And feedback from the builder on the West Van house, it was 30% less. And I could list off, we had less excavation, less foundation work, less concrete, less backfill. We saved the framing cost. There was obviously the engineer had some upgrades we had to make to the framing. But that significant amount of items reduced our building cost by 30% over a new build on that particular project.
Amazing. Thanks, Erica. Okay, so we have just under 10 minutes here to dive into some questions. So reminder to just use that Q&A function. We have one question here that I think came up during your question, Erica, and it was, can you elaborate on smart vapor barriers versus poly?
Yes. Okay. So what happens in a building wall, particularly if you move the dew point and if you're using a vapor barrier at all, you're going to have cavity insulation. The way the vapor barrier works is it takes the airborne moisture and prevents it from traveling through the wall and then halfway through the wall condensing into water droplets. That's what the dew point is all about. That point where it's just masking it. And a smart vapor barrier works kind of like a Gore-Tex jacket. It's breathable, but it also keeps the water out. So the importance of a smart vapor barrier is because in the summer, your vapor drive is actually inward. People are air conditioning, so it's colder inside the house than it is outside the house. So you want that wall to be able to breathe inward through that. It's breathable like Gore-Tex, but it again keeps the water problems outside your wall. Then in the winter, it's colder outside, so your vapor drive is outward. So that smart vapor barrier, I typically, whether it's the exterior waterproof membrane or the interior, I'm always using what they call vapor open membranes. So the ones that the worst thing you could possibly do is put a poly vapor barrier on the inside and then a non-vapor open barrier on the outside. And essentially you're creating a bagel in a plastic bag and it's going to turn into mold and rot. So the breathability of both, and yeah, you'll see it. Try it. Put a bagel, leave it there for a year and see what happens. But the more breathable your wall is, the better it'll handle that moisture. It's able to go back and forth without damaging the wall. If anybody wants to ask me more detailed questions, feel free. I'd be happy to share my contact info.
That's great. Thank you, Erica. Great answer. This next question, Elisabeth, came up right at the end of your presentation, question/comment. I'd like to see something on retrofits on more modern heat pumps, such that central units that can run at minus 20 degrees Celsius instead of 2010 units that are only ran to minus 3 degrees, and see if it's too carbon intensive to do the conversion too early instead of 20 to 25 years.
Fantastic question. It would require some deep thinking about pros and cons here. I'm afraid I don't have one single answer and simple to that, but happy to chat further if you want to reach out. One thing I will say on mechanical systems is the global warming potential of the refrigerants is a big issue. And often not even included in life cycle assessments. So newest research only came out maybe a few weeks ago from a group called MEP 2030, where they look at mechanical, electrical, and plumbing and the embodied carbon of those systems, as opposed to the traditional LCA systems, which is just structure and envelope. And so there is more and more work done related to embodied carbon of mechanical, but what has transpired so far is that it is a much bigger impact than we think. So thinking about, again, on that part of my presentation was simplifying the mechanical systems. It is very, very important, as well as selecting heat pumps with a refrigerant that has a lower GWP. So the lowest option, to my knowledge, is CO2 used as refrigerant, but it's not yet available in part 9, if I'm not mistaken. If someone has more information than me, I would love to hear it. But I've heard of some CO2-based heat pumps that are being used for part 3, but not yet in part 9. Or there might be one supplier, which makes it a little more challenging from a procurement perspective. So yeah, pros and cons, heat pumps, different. The technology is getting better, and they are working extremely well now, even in minus 30 temperatures. Now the question about retrofitting these now or later, I don't have yet an answer for that.
Thanks, Elisabeth.
I offer a thought on that too. In the last year or so, I've gotten involved with the B2E group, that's Buildings to Electric, through the Zero Emissions Innovation Center. So there's these group emails that go out constantly, like every day I'm getting something, somebody's commenting on it. They recently released their revision to the BERM, the building, I forget, building electrification roadmap. And there's so many people on that group that are very much into the mechanical side. That's not my expertise, but they have a ton of information about this and where it's going and how we can get there. They've just come out with this. So If anyone wants to look up the BERM, BERM, it's the roadmap that B2E is been working on for a number of years.
I just dropped the link in the chat too.
Thank you.
Amazing. Thanks both. We are just getting to time, but we have one last comment that came up again at the end of your presentation, Elisabeth, that I'll open it up to anyone to comment on. And just a comment speaking to hemp insulation specifically being a concern. Any thoughts or comments on that?
Depending what concern we are talking about. Happy to chat offline about this. On our project, there was no concern other than it couldn't be used on the exterior walls. But we kept the foundation as well in the concrete slab, and we also built a floor above it and used hemp there as well. Okay, so I see the comment now. Okay. It was answered by Mike regarding the architect engineers being involved. Okay, all good. We're all good. Answered good.
Perfect. Okay, thanks for that. And we're just about at time here. So thank you to everyone on our panel for such a lively conversation and discussion. I learned a lot and it was great. And I'm sure, as mentioned, that if anyone has any additional questions, you're welcome to reach out to our panelists after the webinar. But just to finish up here, a heartfelt thank you to our main funder, BC Hydro, and our webinar sponsor, McDonald Mechanical. It is thanks to these organizations that we were able to offer this webinar free to contractors like yourselves. If your organization is interested in becoming a sponsor and getting involved with future events, we'd love to connect. We'll share our contact information in the chat right there. And then just a quick plug for the Home Performance Contractors Network as well. This is the network that enables your clients to access provincial and utility rebates for heat pump installations, new windows and doors, and installation upgrades. There are other benefits of joining the network, including subsidies for industry-specific training. Feel free to connect with us if you have questions about how to become involved, or reach out to their info@ email, which we will also throw in the chat. Okay, that's it for now, everyone. Finishing right on time. Thanks for taking your morning to join during this webinar. Again, thank you to our panelists, and we will see everyone again soon. Have a great Thursday.
Thank you for having us.
Thank you for having us.
Thank you.